All right, it is 9 o'clock, so we'll get started here. Like I had typed in the chat box, I am not feeling the greatest today. Definitely under the weather. So I'm going to try my best to make it through the whole class today. What we're going to do is we are going to do our matrices stuff on the calculator today. So you will need your calculator. I do not know of an app offhand, like an online version that will work for our matrices. I'm sure I could Google something and try to find something. Um, but we're going to be looking at the calculator today. I haven't had the time to Google how to do this on the calculator, or if there is an online program for free. So I will search that once I'm feeling a little bit better in case you don't have a graphing calculator that you can look at right now. Taking a look at 7.02, are there any major questions from that 7.02 lesson before we begin here today? Overall, the scores were really good on it. Nothing major popped out at me that I had to revisit or reteach. But any major questions with 7.02 before we take a look at 7.03? Okay, now all the stuff that we're looking at here today can be performed algebraically, but it's time consuming. And it can get a little bit confusing at times, which is why we're going to rely on the calculator for the most part. It is going to save us an immense amount of time if we can just punch things into our calculator and let it do all the dirty work for us, so to speak. So today we're going to be looking at multivariate linear systems and row operations. So basically what that means, and before I get too far into the calculator piece, I do want to talk about the Gaussian elimination method real quick here. Basically the Gaussian elimination method allows us to solve a 3-variable system. So however many variables you have present, that's how many equations you need in order to solve. So if we have 3 variables, we need 3 equations. If you were to up the game and introduce a 4th variable, you would need 4 equations to help you solve for those different pieces there. All right. The Gaussian elimination is actually really nice because it's just the elimination method, but you have to perform it multiple times. So that's what's going to make it a little bit tough, is that we do have to do the elimination method multiple times in order to come up with our answer. So we'll run through one of these algebraically, and then we're going to start looking at how we can use our matrices to help us simplify the process. All right, so here's the first system here. And notice that we do have 3 variables in x, y, and z. Therefore, there are 3 equations. Just like the elimination method, we do have to pick a variable to eliminate first. And we're got to stay consistent with that when we start grouping the equations together. And that'll make sense in a moment what I mean by grouping. So taking a look at the system there, which variable is going to be the easiest to eliminate? So the least amount of work possible needed to get rid of the variable. Yeah, I would agree, z for sure. So we have decided we're going to try to eliminate the z. So now we have to take 2 equations at a time. So I'm going to group equation 1 and equation 2 together, and I'm only going to look at those 2 equations. In order to eliminate the z, what do I need to do to one of the equations? So when I add it together, it goes to 0. So what has to happen to either of the equations there? So when I add them together, it goes to 0. We've got to multiply one of them by a -1, and it doesn't really matter which one we do that with. Do you guys have a preference? Do you want to multiply equation 1 or equation 2? Equation 1 it is. All right, and again, there's no wrong answer with that. I'm just going to go ahead and change the signs on everything in equation 1. Equation 2 is going to stay the exact same that we have it. All right, let's go ahead and add these two equations together now. What's a negative 1x plus 3x? Yep, we have a 2y minus 5y. The z's are gone. We have a negative 7 plus 14. All right, now it doesn't look like much, but we did go ahead and take that from a 3 variable down to just 2. We're going to do the exact same thing with the next two equations, so the second and the third. The nice thing about those is that we can just add them together because the z's are going to add up to 0 right away. So if I add those two equations together, looking at equation 2 and equation 3, what do we end up with? So when I add equation 2 and 3 together, what's the result? A 5x minus 7y equals 17. Okay, and Isaias just seconded that, which is awesome. So now essentially what we did is we created two new equations from the bunch. Now with those two new equations, the process starts over. Which variable would you like to eliminate, the x or the y? The x. All right, so if we're going to eliminate the x's, we have to multiply each equation by something. What would you like to multiply equation 1 by? The 5, okay. And you can do a negative 5, Isaias. If you're going to do a 5 in equation 1, you've got to do a negative 2 in equation 2. So the negative sign can either be applied to the 5 or the 2. It doesn't really matter, but it has to be applied to one of them, right? Because you need opposite signs there. All right, I'm just going to do exactly one, but not both. I'm going to multiply through here. Oh, this actually isn't going to be so bad. When we add these together, what are we looking at? Negative y equals 1, therefore y equals a negative 1. Good. All right, so the hard work is basically done now. Because you have a variable solve for, now we're just going and using substitution to find the other two missing variables. So we're going to backtrack to our two kind of new equations that we created here, and let's substitute into one of those to solve for x. I'm just going to substitute into the bluish one, I guess. So substituting back into that, I'm going to get a 2x that would turn into a plus 3 once I substitute in the negative 1 for y. I will subtract 3 from both sides and divide by 2. All right, now that we got another one of the variables solved for, we just got to find that z. So to find the z, we go all the way back to the original equations and we substitute into any of those. I'm going to just substitute into the first one because that looks like it might be the least amount of work that I would have to do. So x is 2, y is negative 1, so that's a 2 plus 2 plus z equals 7. Subtract the 4 from both sides and I get my 3 for z. Now, your answer, instead of being expressed as an ordered pair, needs to be expressed as an ordered triple. So an ordered triple is just what you think, your X, Y, Z, right? So alphabetical order, X, Y, and Z for that final answer. All right, are there any questions with that Gaussian elimination? So we may have seen this once or twice, maybe back in Algebra 2 days, a little bit, but we didn't spend a great deal of time on it. So we are presented with it again here in pre-calc. The good news is that we can use matrices to actually speed the process up, and we don't have to do this all by hand. So silver lining for today's class is that there is going to be a quicker route than having to go through all of those steps. But it's important to see that there is multiple ways that you can solve for a multivariate system like we have here. Any questions with this example? All right, let's get to the fun stuff then, shall we? All right, so just a side note before I go too far, that there are still special cases that can exist, even when we're going to be working with our matrices here. You can still run into the possibility of no solution, and you can still run into the possibility of infinitely many. You're going to run into that no solution when you're left with a false statement. And I'll show you what a false statement actually looks like when we get it on the calculator. And if your variables drop out and you're left with a true statement, then we know that there's infinitely many. And again, I can show you kind of what that would look like when we're working through it on the calculator. All right, so the first thing we're going to introduce you to is something called an augmented matrix. So an augmented matrix is simply just a matrix made up of the coefficients and the solutions in your system. So really kind of basic there. You can take that system that we just had. I think that's the same one. Excuse me. And notice that they just pulled all of the coefficients there and put that in matrix form. Now what you can do with the augmented matrix is you can do something called row echelon form. And row echelon form is basically rearranging and performing operations to your augmented matrix so that it takes on the form of your main diagonal being zeros, or ones, and zeros in front of them. And then you can have basically any number after it. Now, performing the operation so that you can get that in row echelon form helps you basically to get to that last step where you can solve for the last variable. So putting that in your row echelon form allows you to find z, right? Because technically you would have 1z equals whatever number it is over here. And then you can backtrack to help you use substitution. These numbers are just going to be the coefficients in front of the variables, right? So you can use this row echelon form to help you kind of get to that substitution piece and work backwards from there to help you solve for the other variables. Now, if there's a special case, your bottom row might all turn to zeros. Yep, so it's not uncommon to see the bottom row all turn to zeros once in a while. That may represent a special case, and that would be your infinitely many case if that happens. but we need to note that that row consisting entirely of zeros, if there are any, needs to occur in the bottom of the matrix. You can't have that in the top. If that were in the top, then you have to move it down to the bottom to represent that. We can't leave it hanging out in that top row or anywhere else. We got to make sure we start zeroing out the bottom first and then moving things up. Okay, any questions on what row echelon form actually is? So not how to find it, but what it looks like. Okay, now to put a matrix into row echelon form, you have to perform operations so that that main diagonal is consisted of ones, and if you are in row 2 and 3, you have zeros before the ones. So you can interchange any two rows in your matrix, that's all right. So if you see in the augmented matrix that maybe row 1 didn't start with a 1, but row 3 did, you can switch the equations around, right? So you can reorder those equations or switch the rows if need be. So to make it easiest on yourself, obviously you want row 1 to start with a leading coefficient of 1. And if that first equation didn't do that, but another one did, it would only make sense to put that equation that had the leading coefficient of 1 first. Infinitely many solutions are going to happen when that bottom row is going to turn into all zeros. So if we were ever run into that, that's going to probably represent our infinitely many solutions. We will look at an example today of the no solution case as well. So I'll show you, what you'll look like or what you'll run into for that no solution scenario as well as we're working through these. All right, and then in order to get that into row echelon form, you can basically do kind of your elimination method where you add rows together, you multiply through by a row, or multiply a number through a row and then add together. So whatever you can do to kind of manipulate and get zeros in front of your ones on the main diagonal, that's what you can do to get perform those elementary row operations. Now we aren't actually going to do any by hand because the calculator does take so much time and it's already 9:20. You can do it by hand. I think the book goes through an example of what you can actually do by hand to get that into row echelon form. I'm going to spend the majority of my time showing you how to do it on the calculator. All right, so here it comes. On your calculator, I want everybody to find the matrix button. All right, and everybody, if you have a calculator like mine, hopefully you have that matrix button. It's actually in blue, and it's right in blue above the x to the -1 power. So I know that my webcam's a little bit blurry there, but that does say matrix right there. So if I hit the second matrix button, I'm going to get a screen that looks like this. Right, so you can see that there are 7 that pop up, but there's more below it if I keep scrolling down. 7 different matrices that I can edit in here. So we are going to go ahead and scroll over to the edit button. So on the top screen here, using our arrows, I just went over until I got to that edit button. And I'm going to go ahead and edit matrix A. So we're going to go ahead and punch in the augmented matrix for the problem that we see on the board. All right, so I'm just going to hit enter. When we do that, your screen will pop up here, and the first thing you have to tell your calculator is what the order of the matrix is that you want to punch in. So the augmented matrix, let's just figure that out on the board before we actually punch it into the calculator. How many rows are going to be in my augmented matrix for this system. Three, because that's how many equations there are. And how many columns are there going to be? 4. Very good. So as we punch this in, we want a 3 by 4 matrix. And when we do that, your calculator will readjust and give you those spaces needed to now fill in the coefficients for them. So row 1, we're going to go ahead and just place in with the leading coefficients from that equation. So I'll go ahead and give you a moment. Type those in. Make sure you're using the negative sign down here, not the minus sign for negative numbers. I know some people like to favor the negative sign or the minus sign versus the negative. So row 2, it looks like it's going to be 2, 1, negative 1, 0. And then the last row will be negative 1, 2, negative 3, 7. Okay, and then once you have all those entered, and again, I'll give you a moment to do that, we're going to just hit second quit. So second mode or second quit just brings you back to that home screen. So second, and then the button right next to it is the quit button. All right, I'll give you a moment. Go ahead, give me a green check mark when you have that matrix A edited into your calculator. Has anybody ever worked with matrices on their calculator before today? Just out of curiosity? Okay. We've never seen matrices before, at least in the mathematics. Oh, Rebecca has? Good. That's good. If you've had me in previous years, we've never really explored matrices up to this point, so this is kind of new for you, but I know that sometimes it is introduced in Algebra 2, so some people may have seen it in their Algebra 2 course. Ooh, okay. I've never done it on the Desmos matrix calculator, but hopefully that works out for you. I'm thinking it will. Desmos seems to be pretty crafty with all the different modes that they have, and they seem to work most of the time. So it should work for you on the Desmos one. Okay, if you're still typing that matrix out, that's fine. Take your time to do that. I'm going to go ahead and move forward here. You should be on the quit screen right now, right? The blank screen. If you hit that matrix button again, so second matrix, and we come back to this opening screen here, this time let's go to the math button in the middle. So we're going to use our arrow key to scroll over. And now we're in that math window. Look at all the different stuff we can do here. So the first option is DET. That's the determinant. Remember talking about that in 7.02? You can do the determinant of a matrix in this feature here. So if you were to go ahead and edit a matrix and you want to find the determinant of it, you'd hit 1, and then we select the matrix you want to find the determinant of, and it will do that for you. At DIM, I believe that's the dimensions. You guys already know how to find the dimensions, or that might be something else. The identity matrix right there. So if you want to find the identity matrix of something, you can use choice 5. I'm going to keep scrolling down because what we actually want is, if we take a look at A and B, so if you use the arrow that scrolls way, way down, you can see REF and RREF. So REF stands for row echelon form. See, check it out right up here. row echelon form, REF. The one below it is actually going to be more useful to us. That's called reduced row echelon form, and we're going to talk about that reduced row echelon form in just a moment, and that's going to be the one that we use majority of the time, is that RREF button. But since we are looking at row echelon form, I am just going to pop up one to that choice A and hit enter, and we see the REF come up on our screen. So what we need to do now is tell the calculator what matrix we want to put in row echelon form. And so we're going to go back to the second matrix button. So back to the matrix screen, second matrix, and just choose that choice A. So hit enter, because A should already be highlighted. I'll put the end parentheses in there for good measure. But we just told the calculator now that we want to find the row echelon form of matrix A. So I'm going to go ahead and hit enter, and we get a whole bunch of numbers pop up on our screen. These numbers are the row echelon form. So I'm going to go ahead and let's copy these down. So my row 1 is a 1.5, negative 0.5, 0. Row 2 looks like it's 0, 1, negative 1.4, and a 2.8, and that might possibly be rounded. And my row 3 looks like a 0, 0, 1, 3. All right, did you guys get the similar response there for your row echelon form with your matrix A? Awesome. All right, now this isn't the only possibility you can get with the row echelon form. There are actually multiple representations that you can come away with, and it really doesn't matter what these numbers are, and what's going to differ are kind of these values right up in here that I'll highlight. Those numbers can be a little bit different. So if you were to do this by hand, you might actually get different values there than what the calculator did, because maybe you took a different approach to solve than the calculator. But when you start using substitution and using back work, you will still get the exact same answer in the end for your variables x, y, and z. So taking a look at this row echelon form, I know that z is going to equal what number? Z is going to equal 3, because looking at this last row, we know that 1 is the coefficient in front of the z. So technically that stands for a 1z equals 3. Sometimes you'll see augmented matrices have little dots after those leading coefficients to kind of separate what the leading coefficient is and what the answer is. So sometimes you'll see little dots appearing after that third coefficient for each variable there, just to kind of separate the two pieces of the augmented matrix. Now that you know what z is, you can work backwards to help you find y. You would do y minus 1.4z equals 2.8. So you can use substitution there and start backtracking to find the y, and then you can use substitution a second time in that first equation to help you find the x. We're not going to do quite that. What I want you to do instead is let's go back to, so clear out your screen, go back to the matrix, so second matrix. Let's scroll over to the math in the middle again, and this time let's select that reduced row echelon form, so that RREF. So this time we're going to choose RREF, reduced row echelon form. So I'm going to hit enter. And it seems a little bit tedious because now we have to go tell it what matrix we want it to find the reduced row echelon form of, and that means we want to go back to the matrix again, and say take it of row or matrix A. So I'm going to just select the A and hit enter. Check it out. So now it looks a little bit different than the augmented or that row echelon form, right? You have ones on your main diagonal still, but everything after that is zeros, except for that solution piece. So -2, 7, 3. This is what we love about our matrices, because this reduced row echelon form are our answers for each variable. So x is what we put in the first column, therefore x equals -2. Y is 7, and z is 3. So we don't technically have to do the substitution piece and working backwards to find x and y in that setup. It actually does all the rest of it for us, the rest of the solving, I should say, for us. And it tells us what x, y, and z are going to be. So woohoo! Thank goodness for our calculators, right? Did everybody get that reduced row echelon form to come away with -2, 7, 3? Okay. Now, reduced row echelon form, we should all get the same matrix for, but the row echelon form, some of the numbers can be a little bit different. But once you go through the substitution of it all, your answer will come out the same. But the reduced row echelon form, everybody should get that same matrix. All right, and here the next slide is just talking more about that reduced row echelon form and how it's zeroing out the other components in the matrix that are not along the main diagonal there. Okay, the last thing that we're going to talk about today is using our matrices using inverse matrices to help us solve. So if we are given, you can obviously use row echelon form and do one augmented matrix, which I think is going to be the easiest. But sometimes they break it into two different matrices. They break it into a matrix that's dealing with your coefficients, and then they break the second matrices just using your solutions. Okay, and what they'll do is they call the coefficient matrix matrix A, and your solution matrix matrix B. And how they set this up algebraically then is they say you take matrix A times x, which is going to represent your variables x and y, and you let that equal matrix B. Okay. And we can kind of visually see that occurring, right? Because if I were to multiply the A and x here together, we can come away with the coefficient piece at least of our equations up here. So we can see that kind of visually occurring. To get the x by itself, we have to do the inverse of A, right? Because we want to get rid of A. And there's no such thing as dividing matrices. But we do know an inverse. So if I take the inverse of matrix A, I also have to take the inverse on the other side as well. Now here's the kicker. Where you put that inverse of that matrix A matters. We always want it to come before the A and the B original, okay? Because we did see that when you multiply matrices together, the order matters. Right? That was something we saw in 7.02. That kind of took us off guard at first, right? But we always want to make sure that when we are punching this into the calculator, that we put that inverse matrix first and then matrix B second. All right, let's show you how to do this real quick on the calculator. So get back to the matrix screen, and we want to edit two different matrices this time. We're going to We're going to edit matrix A, and we're going to edit matrix B. So I'm just going to edit matrix A first, and A is a 2 by 2. So that's the first thing we have to do is change our order. So it's a 2 by 2 matrix, and I'm going to fill in the values there, the elements. Okay. Then we have to go back and to the matrix screen, so second matrix again, edit. This time scroll down to matrix B. Matrix B is a 2 by 1 matrix, right? 2 by 1. And we want to enter those elements in. Okay, I'm going to give you a moment to go ahead and edit those matrices in your calculator. When you have matrix A and B edited in the calculator, go ahead, give me the green check. Okay, if you're still typing those in, that's totally okay. Take a moment. Let's go ahead and then get A inverse B up on the calculator now. So on the home screen, we're going to want to do, we don't have to go back to the home screen quite yet. All we have to do is just do second matrix to take us back to this screen. And then we want to select matrix A. So you can just do second matrix to come back to this kind of home screen for the matrices and choose matrix A. Oopsie. I hit the wrong button by accident. All right, once matrix A comes up, then we have to use this little button. So we've been hitting it all along, but the x to the -1 power. We want to select or hit that button because that's going to give us that inverse key. So notice that we just did matrix A inverse by hitting that little button on our calculator. So there is that button again right under the math. That gives you that -1 power. All right, now we got to go enter matrix B. So go back to matrix screen, scroll down so that B is highlighted, hit enter. It's up on the screen. Go ahead and hit enter again, and it's going to give you the 1015. So 1015 is your solution for matrix X here. So we'll see a 10 and a 15. So basically that means X equals 10 and Y equals 15. We do want to write that as an ordered pair, so we don't want to lose sight of how we need to express our answer, but it gives us the answer in the calculator there. So using the inverses there is another option on getting X and Y. Again, you could have done this using reduced row echelon form, and kind of only doing that with one matrix versus two. But it is another process here. Any questions with this using the inverse for the matrices? Okay. Here's another one, another example that wants you to solve a system using inverse matrices. Let me just take a look. Yep, we want to go through this one because I think this one, no, it's not. Hold on. I'm gonna jump around to this one. Yeah, I think this is the one where we're gonna get an error. So let's take a look at this. It does say to use Gaussian elimination, which is kind of that long process that we started off with today. We're gonna just use our matrices to speed it up. So we are going to use our matrices here to come away with our answer. Let's use the inverse matrix just so that we can get a little bit more familiar with the output here. So if I'm going to use inverse matrices, I've got to create a matrix A and I've got to create a matrix B. Matrix A is going to come from the coefficients of my equations there, or the terms of my equations, I should say. And if you guys want to get a head start on entering these into the calculator, go for it. Matrix B is created from the solutions. Okay, so now we just got to go to second matrix, over to edit, and then enter matrix A, which is a 3 by 3 this time. And then again, second matrix, edit, B, which is a 3 by 1 this time. Okay. You'll get faster with entering these matrices too. If you feel a little bit kind of pokey right now, you do get a lot faster once you keep doing them over and over and over. All right, so what we need to do on that home screen then is we need to take the inverse of matrix A and multiply that by matrix B. So again, to find the inverse, we just select matrix A. Oopsie. I don't know why I keep doing that. There we go. Select a matrix A. There you go. Yep. And then hit the little inverse key. Find matrix B. Whoa! What happened? We get an error. So if we get an error, that means we have a special case that's occurring. Chances are it's probably going to be your no solution case. It says no inverse. Ooh, yours says no inverse. That's pretty cool. Mine says singular matrix. So that means that one of the rows is being canceled out for that singular matrix piece there. So we definitely know that there's going to be something weird going on. There's a special case happening. This is going to be the case of a no solution. And to get a clearer picture of what's happening, you might want to use your row echelon form. So, or even your reduced row echelon form. So if I go back to matrix A and I edit that one more time so that I make this a 3 by 4 matrix, and then I can just enter in that last value, which is your 14, -3, and 4. So if you go to matrix A and just edit that to make it a 3 by 4, and then just throw in that last column of solutions. And then if we try to go to the math piece and do our reduced row echelon form of that matrix A that we just edited again, we can get the actual values there. So you can see that last row, we have 0, 0, 0, 1. And this is actually reduced row echelon form as well, and we don't have all the zeros on the other column, like that third column. We don't have zeros above that. That's a problem as well. And that's because that last row threw an error. So we can see that you get 0 equals 1 in that last row, which is a false statement. So 0 equals 1 is a false statement, which means that there is no solution there. So there's an example where we, I know, right, run into one of those special cases using our matrices on our calculator. So you'll run into an actual error message, or if you're doing that row reduced echelon form, you'll see the zeros with just the solution at the end, and that's a problem. All right, I know I kind of ran out of time, but I think we hit all the crucial information here. I always plan way more than I need to. Um, you may actually see some of these operations here on your homework assignment. I can't quite recall if you will or not though. If you see something like this, 4 times row 1 plus row 2, whatever the second row is that they're mentioning, or kind of that last row, that's what you're replacing in the matrix. So what this is basically telling you to do with this augmented matrix is take 4 times the element in row 1 and add that to row 2. So when I do that, 4 times 1 is 4. 4 plus negative 4 becomes a 0. So I'm technically replacing row 2 with the 0 for that first one. And then I do that with every other column as well. 4 times 6 is 24. 24 plus 9 is 33. That sound right? And then the last one, 4 times 3 is 12. 12 plus negative 1 is 11. So technically that row 2 is going to be replaced with 0, 33, 11. So we didn't do it by hand, but you may want to go back and see how to put something into row echelon form. Okay, because we skipped that. We relied on our calculator to do that for us, but this is part of the process on getting an equation into row echelon form. Okay, I think that's it. Yep, because then that's row echelon form. We did that on the calculator. Reduced row echelon form we did on the calculator. Yeah, and that brings us to the end of 7.03. Woohoo! All right, any major questions with the matrices and how we can use our calculator to help us with those?